Welcome back to the System Design Interview Roadmap. In our previous lesson, we explored what happens when your distributed system becomes a crime scene, where individual components report healthy status, yet the entire system fails. Today, we're diving deep into the detective work required to solve those complex puzzles. This lesson, issue 132, focuses on advanced distributed system debugging techniques. It's about shifting your mindset from fixing code to reconstructing events across a vast interconnected landscape. By the end of this lesson, you will be able to identify the unique challenges of debugging distributed systems compared to monolithic applications. You'll also learn to explain the critical role of correlation IDs in tracing requests across service boundaries. Furthermore, you'll be able to describe how temporal, debugging, and state reconstruction provide insights into system failures. Finally, we'll equip you to recognize advanced observability strategies and enterprise debugging patterns that uncover elusive bugs. This isn't just theory. It's about mastering the hidden art of distributed debugging to build more resilient systems. Let's begin our investigation. When a request travels through a distributed system, it hops between many services, databases, and queues. Without a way to link all these disparate events, debugging becomes an impossible maze. This is where correlation IDs come in, acting as your digital breadcrumbs. They are unique identifiers assigned to a request at its entry point, and then propagated across every subsequent service call and log entry. Think of it like a unique case number assigned to a customer's inquiry that follows it through every department it touches. This allows you to trace a single transaction's journey from start to finish, providing a complete picture of its interactions. But it goes beyond just tracing requests. Advanced systems use multi-dimensional correlation IDs, encoding not just the request path, but also user context, feature flags, and deployment versions. Netflix, for instance, found that this approach drastically reduced their debugging time by enabling them to reconstruct not just what happened, but why a system made specific decisions. It's about building a rich context around every event. This fundamental technique transforms scattered logs into a coherent narrative of system behavior. Next, let's explore how timing plays an equally crucial role. Traditional debugging often assumes a linear, synchronous flow, but distributed systems are inherently asynchronous and concurrent. This is why temporal debugging is a game changer. Instead of debugging by service boundaries, you debug by